Good day everyone and welcome to my presentation. First of all, let me introduce myself. I am Said Fadlo. I am PhD student at Ensam Hassan II University in Department Structural Energy, Engineering, Intelligent Systems and Electrical Energy. Today, I would like to present our work titled Energy Estimation Based on Path Tracking for Differential Guide Mobile Robot.
So this is the outline of that I'll be going through as the presentation progresses. Modern mobile robots have many advantages: high efficiency, reduced cost, customizable, upgradable. Their main disadvantage is a limited energy resource because of a relatively small capacity of batteries. To deal with this inconvenience, two approaches are invested according to the literature. First one is achieving an optimal design on the hardware. The second is optimizing the software and motion strategy. Recently, more attention has been paid to the design and control of mechatronic and robotic systems by considering the minimization of the consumed energy. In this regard, multi-domain dynamic simulation is becoming an issue in the design of mechatronic systems where advances are foreseen only if the mutual interaction of different parts of the system is well understood.
Emergent mobile robot applications often require tracking complex trajectories over a long period of time. To be useful, the tracking has to be energy efficient to avoid having a major impact of the battery life of the mobile robot. The problem of modeling the power consumption of motion sensing, communication and embedded hardware for mobile robots is a complex work that needs appropriate tools. Two research opportunities were identified. A model for wheeled mobile robot system can be designed to estimate the needed energy to accomplish efficiently the tracking path missions. The modeling environment provided by MATLAB software with Simscape can be a valuable tool to specify the most naturally different uses of energy in the mobile robot system according to the track path strategy.
In this work, we consider the Pioneer 3DX, a differential wheeled mobile robot. Our methodology consists in the following steps. First, represent the mobile diagram. Second, represent system equations. Third, convert to the Simscape and Simulink model block. After that, simulate the model, then analyze the results, and finally validate the model. Before an energy model is developed, it is extremely important to understand the kinematics of differential drive robot system. A differential drive robot has two driving wheels which are attached to DC motors and caster which is added for balancing. The rotation of the motors causes the wheels to rotate, producing linear and angular motions of the robot. A kinematic model is shown as follows in Figure 2. The linear and the rotational velocity of the robot are given by the following equations. To complete our study, we need a DC motor model. The DC motor behavior is characterized using an equivalent circuit model. The differential equations that describe the dynamic model are:
After analyzing all compounds, the total energy model equation is presented as follows. When the kinetic energy of the robot at any time can be expressed as equation 5.
in this section, we will present several simulations performed with Simulink and Simscape tools for evaluating the proposed model, as shown in Figure 4. The blocks above are a serrated model of a motor drive circuit and DC motor controlled with a voltage input. On the right side we have geared box block. The parameters used in our simulations for DC motors are listed in Table 1, and for mobile robot are in Table 2.
In this section, three scenarios will be presented. In the first scenario, a straightforward path is considered. In this case, the mobile robot is located along the x-axis at 0, 0 and tracks the path as shown in this figure, with the linear reference velocity equal to 0.5 meter per second, and the angular velocity equal to 0 radian per second. Our simulation in Figure 7 shows that the time taken by the mobile from the start location to reach the goal is 81 seconds, and approximately 700 joules are needed to achieve the mission. In the second scenario, a square path as shown in this figure by red crosses is considered. In order to evaluate the influence of the linear and angular velocities on the tracking path, three tests were performed. Here we have the trajectory in blue traced by the mobile with v equal to 0.5 meter per second and omega equal to 0.05 radian per second. In this case, the average cross track is greater than desired. Naturally, this leads to excessive energy consumption as shown in Figure 9. In reverse, results of the second and third tests show a good fit to the square path. This is obtained by increasing the angular velocity of the mobile on sharp turns. It can be seen from Figure 12 and 13 that there is a trade-off between achieving a minimum time trajectory and saving energy if we consider this path tracking strategy. Finally, circular path tracking performance are shown in Figure 14 and 15. We can conclude that simulation results show that the model predicts the trend of the power consumption by estimating the kinetic energy of the mobile robot with specific path tracking strategy. The energy modeling method presented in this work shows that there is a trade-off between achieving a minimum time trajectory and saving energy. The physical approach with Simscape tool and optimization techniques can be investigated to design and manage the power consumption of wheeled mobile robots.
Thank you for your attention.